Let's talk about exact differential equations. And let's first see how these are derived. We can have some curve in the plane defined in that way that some function is constant. For example, if our function would be y minus x squared, we would get that y is x squared plus some constant, so we would get some kinds of parabola. On the other hand, if the function would be x squared plus y squared is a constant, we would get some circles. And if the function of y would be a little bit more complicated, we might have something like this. We might have some curves that are better expressed in the way that x is something. Let's then consider that we have some point which travels on the curve as time t changes. So we can write this equation. And let's differentiate this on both sides with respect to t. F has two variables, so the total derivative will be looking like the linear approximation. We will take the partial derivatives of f and we'll multiply them with these derivatives of the inner function. Now, if here we denote the partial derivatives in this way, and we multiply with dt, we get this kind of equation. And if we would divide by dx, we would get the equation into this form. These kind of equations where m and n are obtained as partial derivatives of some function. These equations are called exact equations. The solution will then be some curve in the plane. Now let's start from the other direction. What if we are given this kind of equation? Well, if there exists some function f that we can express m and n as partial derivatives, then the solutions of this equation are of this form. And the equation is called an exact differential equation. If we would take our parabolas and we would form the function, then the partial derivatives we could calculate and we would obtain this kind of equation. So this equation will give us solutions to those parabolas in the plane. Now this equation seems to be separable, so we can solve the equation nicely. If we would take our circle and form the corresponding equation, then again this equation would be separable and we would find the circles from here. In the same way, the third example what we were discussing, it would yield a separable equation. Well, let's see this example. If we would have this kind of curves, we could calculate the partial derivatives and we could form this equation. And now in this equation, x and y are found in so many places that this equation is not separable. So if we were given this equation, how would we know that if this equation is exact? We would want m and n to be some partial derivatives of f. If we take partial derivatives of these in such a way that we will have the derivative with respect to x and derivative with respect to y, then usually we can swap the order of these derivatives. Usually f differentiated with respect to y and then differentiated with respect to x is equal to f differentiated with respect to x and then with respect to y. So we will get that these functions need to be the same. We get criterion for the exactness of differential equations? Well, if we have the equation and we find that it satisfies the criterion, it means it is an exact differential equation, then how can we find the function f? Well, we should take the thing what we want. We want that m is the partial derivative of f in this way. And now if we integrate this on the both sides, we would get an expression for f. In the same way, from the equation of n, we would get an expression for f. Now, while integrating with respect to x, we can get some constant which depends on y. And while integrating with respect to y, we can get some constant which depends on x. So, the goal is to write both of these expressions and then choose the constants in that way that these expressions are equal. Let's study this equation. There is the derivative of y. Let's call the coefficient of that n. And let's call the other terms m. Derivative of m with respect to y would be equal to this. Derivative of n with respect to x would be this. We see that these derivatives are equal, so our equation is exact. If we take m and we integrate with respect to x, then y over y becomes x over y, and 1 over x becomes natural logarithm of x, and as the integration constant we can have some constant which depends on y. Let's then integrate n with respect to y. The first term would give x over y, and the second term would give the natural logarithm of y. And we would have an integration constant which depends on x. When are these two expressions equal? Well, we must have that the thing what depends on only on x in the second equation is equal to e to power x plus natural logarithm of x. In the same way, the constant depending on y needs to be this natural logarithm of y. So, for example, if we take the first expression and we just add the natural logarithm of y there, we will get our solution. We find our function f, and the result is that f is a constant. Let's have one more example. So this thing here should be n, and this thing here should be m. And we need to calculate the derivative of m with respect to y and the derivative of n with respect to x. Let's see. The derivative of m will be 6xy squared, and the derivative of n will be 6xy squared, and they are found to be equal. So we know that our equation is exact. Equation star is exact. And we would want to find now the function f in such a way that if we differentiate f with respect to x, we get m, and if we differentiate f with respect to y, we get n. So how should this function f be? We get two expressions. Well, let's take m and let's integrate it with respect to x. We get that we should have something like this, plus some constant which might depend on y. And let's integrate n with respect to y. What will we get? We will get something like this, plus a constant which might depend on x. And now we see that this constant depending on y, it can be this y to power 7. So our function will be like this. Here's our function f, and the solutions are of that form that this function f is a constant. Now we know how to solve these exact equations. We have the criterion to check if the equation is exact, and then after that we can make these expressions and make them to be equal.